So in this first question, we have a saturated aqueous solution. We have magnesium metanoate. This is talking about mass solubility. So that is mass solubility. It's to do with the mass dissolved in 1 dm cube of the solution, meaning to say in water at room temperature. The exact solubility can be determined by doing titration. You titrate it against KMnO4. During the titration, the metanoate ion is oxidized to carbon dioxide, and I just want to remind you of something, that you know that metanoic acid is can also be oxidized to give you CO2 and H2O using acidified potassium manganese 7. So metanoic acid, despite being a carboxylic acid, it can be oxidized, okay, because of the presence of the hydrogen on the carbon of the acid. All right, so this bit actually makes it able to be oxidized further to just give you carbon dioxide and water. This is quite a common P53 qualitative analysis result, because you can test for acid, but you can also test it with acidified manganese 7. When you heat it up, it should go from purple to colorless as a result of this oxidation process. All right, and a lot of students still thought that it's a carboxylic acid and therefore cannot be oxidized, but actually in the AS specification on carboxylic acid, if you look it up, it specifically stated that you should know about the oxidation of metanoic acid, and the other one is ethane dioic acid. They are both under AS specification, and they can and will ask you in an A2 paper, such as paper 4, or in this paper, which is even a planning paper. And because that is possible, you can imagine metanoate ion being a deprotonated form, HCOO-. It's basically a deprotonated metanoic acid. You can of course oxidize it because you still have that hydrogen on the carbon of the metanoate, so you can oxidize the carbon dioxide and water as well. And in doing its job as oxidizing agent, itself is reduced from Mn plus 7 to Mn plus 2. So this is what you have. You have a saturated. Okay, saturated means you dissolve as much of it as possible in water, and then you filter off the rest, so that, because some of them are insoluble, so you filter off whatever is insoluble, and then your solution is basically saturated. Okay, it's the maximum amount of solid that dissolve in a fixed volume of solution, which is mostly just water. And of course you have this KMnO4, which is 0.0200 mole per dm cube. We are doing titrations, so the concentrations here are pretty accurate to 3 significant figure, so we need to be aware of this kind of thing. Yeah. Now you need to write half equations, so that is plural, and bear in mind that you are not given data booklet in paper 5. You should really know how to write the half equation of MnO4-. In the presence of acid, it will gain electrons, because as I mentioned, that is reduction. And as you have known from IGCSE or O-level or your GCSE, you know reduction is gain of electron, so it's not your first time doing that. And they even tell you what you will get, Mn2 plus, and you will get water. Balancing equation, there's 4 oxygen, so if you put 4 oxygen there, there is 8 hydrogen, so you should put 8 hydrogen there. The atoms are all balanced, manganese, oxygen, and hydrogen are balanced, but your charges are not balanced. This one has no charge, this one has a +2, so overall there is a +2 on the right. This one has a -1, there's only one of it. This one has a add plus, +8 minus 1 is +7, +7 become +2. You need to add 5 electrons, alright? And then you will also have HCOO- going to CO2. Bear in mind that this gives you the CO2, but there's no hydrogen. So we need to think about, before we think about hydrogen, we also need to think about electrons, because this is the reduction, meaning to say the oxidizing agent must oxidize the metanoate. So this is the oxidizing agent. You can oxidize the CO2. Oxidation is loss of electrons, something you have learned from many years ago. All right. But in doing so, we can get the negative charge, yes, but we should balance the atom first. Carbon can give you carbon, oxygen can give you oxygen. Hydrogen, that is a big problem, hydrogen, all right? Do we give off H plus or do we give off H2O? Okay, let's try with H plus first. If I have H plus, then I would balance out the charge, meaning there's no charge, and there will be a -1. So I don't think it's H plus. I think, is it H plus? I think it's H2O. Maybe. I think so. Is it H2O? Let me see. No, I think H plus would be okay. But if I have H plus in acidic condition, I can have H2O because my atoms are nice and balanced already. So by putting a H plus, my hydrogen is balanced, but I will have a -1 overall. I will have 0 overall. So +1 plus how many electrons will give me -1? I need 2 electrons, right? So +1 minus 2 give me -1 overall. That will balance out that thing there. So you can see there are 5 electrons involved for reduction, 2 electrons involved for oxidation. When you combine these two equations together, you need to do something that you did in primary school mathematics. It's called LCM, lowest common multiple of 5 and 2. Then this equation will be multiplied by 2. This equation will be multiplied by 5. You get 10 electrons here. You get 10 electrons here. The rest of them multiplied by the correct number with the LCM. And then, yeah, you just add them together and the electrons will cancel. That's what it means in your specification under redox changes. Use changes in oxidation number to balance chemical equation. So whatever electrons that you have gained must come from whatever you have lost. Alright? So this kind of paper 5 common stuff is always about making a stock solution or dilution. So here, well, it's not a dilution question. It's not a making a stock solution question. It's basically a calculation question. You want it in mole per dm cube for the saturated aqueous magnesium metanoate, okay, and the metanoate ions present in this solution. So be very careful there. There are 2 things there. So if we know that mole is equal to gram over gram per mole, mass over mR, right? The units cancel out. Bookkeeping, yeah, since you are year 9 already. Therefore, if I divide by dm cube, so if I divide this by dm cube, it becomes mole per dm cube, then I will do gram divided by dm cube. Then that is my other relationship, okay? So I was given the question in gram per dm cube. So what I can do is I can convert gram per dm cube into mole per dm cube if I know the mR, which I can work out because despite not having periodic table, they give us these atomic masses there. Alright, so I guess that's not my part 1, that's just my background, year 9 or year 10 calculations, I guess. So what I have is I have magnesium metanoate. What is my magnesium metanoate? There is magnesium HCOO twice, because magnesium is a divalent cation, so Mg2 plus. The LCM of 2 and 1 is 2, so you only need 1 of these, but you need 2 of these to balance out the charge of +2, because each of these is -1. Alright, so the mR of that will be 24.3 plus 2 times 1.0 plus 12.0 plus 2 times 16.0. So I got 114.3. Then the mole per dm cube of the saturated solution, therefore the mole per dm cube is equal to the magnesium metanoate has a solubility of 150 gram per dm cube, approximately 150 gram per dm cube, divided by the molar mass, which is gram per mole. Hope you can see the bookkeeping properly when I've written out the units like that. 1.312. Oops, sorry, the gram cancel out, so what I get is mole per dm cube. I don't know, I mean, they're a mixture of 2 and 3 sig fig. So I can probably give this to 3 sig fig to be appropriate. But that is just for the first part, that is for the magnesium methanoate. And we want concentration of the methanoate. Okay, so be very careful. Assuming it is soluble, which it is, saturated solution, that will give you Mg2 plus HCOO minus. That will give you 2 of it. So because you are in the same volume, because this dissociates to give you this, if you know the mole per dm³ of this is 2 times the concentration of that, because one of these give you 2 of that when it fully dissociates. Therefore, the concentration of HCOO minus the methanoate, the concentration of the methanoate is going to be 2 times 1.31, which is 2.62 mole per dm³. Again, because I use this 3 sig fig, so the final answer is just simply in 3 sig fig. Alright? So in order to obtain a reliable titer value, we need to dilute. So this is dilution. They don't ask you to make a stock solution, but you do need to do a dilution. Okay? How would you accurately take out 5.0 cm³? Alright? So this is about accuracy. So what you could do is you could use a burette, alright, to take out that particular thing. So we know this is the concentrated or the saturated magnesium methanoate, okay, of which the approximate concentration is roughly this much, but the concentration of the methanoate is twice that, alright? And then you need to take out some of it, and then you make up, well, they don't tell you how much you make up, but you want 50 times more dilute, alright, 50 times more dilute. So dilute by 50 times, alright. What was the concentration that we take out? So this was 1.31 mole per dm³ for the MgHCOO twice, because they say it's of the saturated magnesium methanoate, and you are diluting the saturated magnesium methanoate. You are not diluting the methanoate. Okay, so 50 times refer to diluting this. All right. So 50 times mean 1.31 over 50. Okay, mole per dm³, mole dilute. If I start by doing my calculation, I can think about if I do dilution, I just add water, right? So my concentration is different, but my mole will be the same. When I say the mole is the same, I mean the mole when I take out the 5 cm³, not the whole batch. Yeah? When I take out 5 cm³ of it, when I have 5 cm³ of that, I already take it out, 5 cm³, I just add water. Well, in fact, I don't just add water, I add distilled water, because if I just use any water, then might contain dissolved minerals. And what do I have? I'm doing titrations that involve ions, and dissolved minerals or dissolved ions present in just water or tap water would have disturbed or might have disturbed or might have interfered, might have made my titration less accurate. All right. So in terms of calculation, so the mole is the same. So it's a C1V1 equal to C2V2. So meaning to say, my mole of the MgHCOO twice saturated is equal to 5 times 10, 5.0 times 10 to the minus 3 times 1.31 mole per dm³. So they give me 6.55 times 10 to the minus 3 mole. And I know the mole is the same in here, but it's more dilute, alright? It's more dilute, so 6.55 times 10 to the minus 3 mole is equal to, I want the concentration to be 50 times more dilute. this is mole per dm cube, then times the volume of the diluted solution times 10 to the minus 3, because this is in cm cube, times 10 to the minus 3, okay, times the concentration, which has been diluted 50 times, is equal to the actual mole. Okay, so therefore the volume of the diluted solution is equal to, well, rearrange your formula, that times 50 over 1.31 times 10 to the minus 3. And I get 250 cm cube. Exactly. Well, at least that's what my calculator showed me exactly. Alright. And that seems to be a good sign, because making up to 250 cm cube is nice and easy with a 250 cm cube volumetric flask, something you will have known, yeah? But this question is not about making out the solution, it's about how would you accurately measure out. So use a burette to measure 5.0 cm cube. In fact, it's 5.00 cm cube, because you know burette measure up to 2 decimal places, yeah, to plus minus 0.05 of the saturated magnesium HCOO twice solution, and into a 250.0 or 250 cm cube volumetric flask. Alright, and then top up or add up with distilled water to the 250 cm cube mark, and finally stopper the volumetric flask and then shake to mix well. So that is how you dilute it. Okay. Okay, let me just fix up one of my handwriting there. Mix well. Alright. So next bit, before you carry out the titration, you must add some dilute sulfuric acid, because as you can imagine, why is this necessary? Your titration involved the MnO4 minus, right? If you think about what are the solution that you have been provided, you have been provided with aqueous potassium manganate, but this one is not acidified. So that one is not acidified. And what do you need? You need the oxidation in acid solution. So without the acid, this will not happen. Without the acid, this will not happen. Okay, so we need the acid. So in the two half equation shown above, or written above, we need acid H plus to make the redox. We know it's an oxidation and reduction reaction, so it's a redox reaction work. Okay, so we need it to work, and since the aqueous KMnO4 provided above is not acidified, therefore need to add the H plus or the acid prior means before, okay, prior to titration, or you can use the word before your titration. All right, but that is the first part, whether it will affect the result of titration or not. Okay, so in this titration, in this kind of redox titration, the acid is always in excess. Yeah, the acid is always in excess, so it does not matter, so it does not affect the titration at all. Because when you think about it, if your acid is limiting, then what is the point that you're titrating this with this? Because one of these will be exact, Alright, and one of these is something from the burette that you're trying to work out. So this thing is always present in excess, such that one of these and these are limiting. Alright, that will affect your titration, but not the acid, because the acid is always present in excess. So that's why we always measure the acid using a measuring cylinder, because there's no need to be accurate when it's in excess, when it does not affect your titer at all. So the potassium manganate 7 is added from a burette into the magnesium methanoate conical flask. This is your titration. So this is from the burette, so your purple is in burette. So what would you see at the end point? Alright, what will you see at the end point? So you gotta bear in mind, yeah, this is your purple in the burette. You have magnesium methanoate in the flask. So the moment you drop the purple KMnO4 into here, the KMnO4 would have oxidized the methanoate, and the KMnO4 would have gone to this Mn2+, which is colorless or pale pink, very, very pale pink. That's why it looks colorless. But inside your conical flask, it will be colorless, because as soon as this comes into this, it forms this, so it will be colorless. When all of this is used up, then one drop of this will not go to this, it will stay as this, then it will be purple. That's why you need to think about what would you see if you are doing this, you know, gotta always think, right? So it's from colorless to purple, because what would you see in the conical flask? In the conical flask, they don't ask you to explain, but essentially at the end of your reaction, you have the excess KMnO4 that will make it purple in the conical flask. But we also need to be very careful. This is very deep purple in the burette, so you don't really see deep purple in the conical flask because you only have one drop extra. Okay, so very light purple, or sometimes people will just see, you know, like when you have a lot of colorless solution and you have one drop of the purple solution, you will see maybe I say very light purple. Okay, very light purple or pink. The pink is not necessarily the Mn2+, yeah, because you will have a lot of Mn2+, which are mostly colorless of very faint pink, but what you will see is that it will become a bit darker, because now you have that one extra drop of the KMnO4 that hasn't gone to the Mn2+, right? But what you will not see is, you will not see it as dark as the thing in the burette, because you only have one extra drop, because you are very good at doing a titration. You only have one extra drop, and then there's your endpoint. Alright, so you don't see the very dark purple you see in the burette, but instead you see a very light purple as a result of one extra drop of that very purple solution into the conical flask, which mostly contain a colorless solution. So next bit is about calculation. So you have 25 cm³ of that diluted solution. You need that much potassium manganate 7. They give you the mole ratio, so you can use that. Use this information to work out the concentration of that. So if you have the mole of that is to the mole of MnO4 minus, that is 2.5 mole reacts with 1 mole. That is the information given. On the top is for the methanoate. So the methanoate is what you dilute, and the concentration is of the diluted methanoate. So that's 25.0 times 10 to the minus 3 times HCOO minus diluted. Remember, this is the ion, not the whole methanoate thing, yeah? The bottom is MnO4 minus, that's 25.50 times 10 to the minus 3 times 0.0200. So your HCOO minus diluted, remember you diluted it 50 times just now, yeah? You rearrange it, so you move all of this up there, and then you move this down there. You keep this on this side, which I've just rearranged to this side. If you can't see what I'm doing, I'm going to just write it out in one more step. Okay, do whatever it takes in order for you to see what is going on. Okay, some people will need more steps than other people, so don't compare yourself with other people. This is 3 sig fig, this is 2 sig fig, this is 4 sig fig, 3 sig fig. I don't feel happy because this is what my calculator showed me. I don't feel happy leaving it like that. I will add it to 3 significant figure. This is concentration. This is concentration to 3 significant figure. All right. So use your answer to, well, part 6. This is part 7. Part 6 is this. To calculate the concentration of the saturated solution of the methanol. All right. This is of the saturated. Remember earlier we have MgHCOO minus is to HCOO minus is one of these, will give you 2 of these. So therefore, the mole of magnesium HCOO twice is equal to half. Well, I can show you. Okay, this is from the mole ratio. Therefore, the mole of MgHCOO twice is half time 0.0510. And I get 0.0255 mole per dm cube. This is in the diluted solution, because this is in the diluted solution. All right, so this is in the diluted, this is in the diluted. Be very careful. Just now we drew our diagram because we wanted to see exactly what's going on. We dilute by 50 times. I have worked out the mole of the magnesium methanoate in this diluted solution. So the actual concentration of the saturated solution is 50 times more concentrated, because this is diluted by 50 times. So going this way, it's 50 times more concentrated. All right. So therefore, the mole of the MgHCOO twice concentrated is equal to 50 times the dilute one, which is 50 times 0.0255. I get 1.275. This is mole per dm cube. But 3 significant figure. Okay, so I nearly fall into that. 1.28 mole per dm cube to 3 significant figure. All right. So some students were confused because they forgot the dilution. They forgot the 1/2 factor, which was actually covered in the earlier question. Why do you think it's important to label dilute and concentrated? Why do you think it was important to draw some simple diagram, even though I'm not a very good artist at all? All right. So the solubility of magnesium methanoate can be determined at higher temperature using SAM titration. So determine how the concentration of that varies with temperature. So that is what you are changing. Okay, independent variable is what you change. So our independent variable there is definitely the temperature. Your y-axis is what you measure. Okay, so why are you so dependent? The y-axis is the dependent variable. And what are you measuring? This is what you want to find, right? Concentration of that saturated magnesium methanoate, and that concentration can be in gram per dm cube. But when you work it out from the titration, this will be in mole per dm cube. So essentially we are working out for the concentration of the saturated magnesium HCOO twice in mole per dm cube, because that's what you're measuring from your titration. All right, and because that concentration is in mole per dm cube, it will tell you the solubility of the magnesium methanoate in 1 dm cube. The solubility of that can be determined at higher temperature, can be determined So maybe I should put this down here. Okay. But I mean concentration of saturated, that essentially tells you the solubility, because how much of it dissolve in 1 dm cube. The unit of this, how much of this dissolve in 1 dm cube. So I can imagine both of them will be accepted. They have the same unit, they have the same meaning, okay? So both of these you can express it as the mole per dm cube or in gram per dm cube, alright? I really think both of these would have been accepted, okay? But they did say that you want to determine this, so perhaps this is probably more accurate than this, but this would tell you this as well. The more concentrated it is, meaning the more of it dissolve in the solution at that temperature. That is also the same as solubility. So next bit is the equilibrium. So they're saying that in actuality this is an equilibrium. So what does it tell you about delta H? Alright, you gotta explain your answer. This is your Le Chatelier principle. It's from your AS, from your O level in GCSE as well. The solubility increases with temperature. So as temperature increases, I'm going to explain first because I find it easier if I think out loud first. As temperature increases, more magnesium HCOO twice becomes soluble. So which side of the equilibrium are we favoring? So we favor the forward reaction, meaning more of it dissociates to the right hand side. So equilibrium shift to the right. When the equilibrium shift to the right, you get more of them dissolving. That's what it's saying. The solubility increases, you get more of them dissolving at higher temperature. So this means the system or the reaction shown above, or the equilibrium, must have tried to oppose the change, which is increase in temperature. The change is increase in temperature, and therefore it would have tried to oppose the change by decreasing temperature. That is your Le Chatelier principle. So it goes forward to decrease temperature. So it goes forward, it shifts to the right to try and decrease temperature because it wants to oppose the change, which is increase in temperature. Hence you can say the forward reaction must absorb heat. The forward reaction must absorb heat. Therefore delta H, because that's what they're asking. Therefore delta H forward is endothermic. It is greater than 0. Let's look back at this. So if the forward reaction is endothermic, the forward reaction absorbs heat. When you increase temperature, the reaction, the equilibrium, will try to oppose the change by decreasing temperature. So it will absorb more heat. When it absorbs more heat, it will shift to the right. It will make these dissociates more into the ions. It will make it more soluble. So I'm correct, okay? A student used the same titration method, but this time to measure concentration of saturated solution of barium metanoate. So here the difference is really barium versus magnesium previously, alright? But this time they say, when you acidify it, before you do the titration, do not use dilute sulfuric acid because it makes it difficult to do. I hope you know that barium 2 plus aqueous plus SO4 2 minus aqueous can give you barium SO4 solid white precipitate. So H2SO4 aqueous precipitates out barium sulfate, okay? And this, you know, when you form precipitate, is white in color. So this makes insoluble salt in the titration. Insoluble salt before you even start the titration, okay? This makes an insoluble salt, makes it difficult to see endpoint very clearly, because they are not saying that why is impossible, they're saying why is it difficult. When you have a white background, a white solid, usually in titration, when you swirl your conical flask, you're getting a solution, right? So you want to see that one drop of the purple solution into the colorless solution in the conical flask. It will go very, very faint purple, very, very faint pink, which is noticeable because of the one extra drop of the purple KMNO4. So it might be more difficult, especially when you get a lot of solid in that solution mixture at all. In fact, it's not even a solution, it's like a suspension, okay? So this is your group 17 hydrogen halide being formed from the gaseous hydrogen iodine, gaseous iodine. This is an equilibrium. So they really like the equilibrium in this paper, okay? They want Kc. So Kc is to do with square bracket concentration. You square it because there's 2 in front of the stoichiometric balance equation. And then you divide by the concentration of the reactants, okay? And you will know there are no units here because the units will be cancelled out. They haven't asked for the unit, obviously, but in a theory paper, they really like to ask for the unit. So there's mole per dm cube square at the bottom. They cancel out, so it give you no unit. I don't think you get any marks for doing this, but I'm just showing you that there are no units, as they like to ask you in an MCQ or even in a structured theory paper, okay? So if the starting concentration of both the iodine and the hydrogen was A mole per dm cube, and you get 2y mole per dm cube of hydrogen iodide. So this is a kind of a very common equilibrium KC kind of question, yeah? So the best thing you could do is really set up an equilibrium table. So I know the equations are given above, but I want to set up an equilibrium table so that I can write out, like things like initial concentration, where I have A and A because both the iodine and hydrogen was A mole per dm cube. I have nothing of the Hi, and then at equilibrium, I would have 2y mole per dm cube of Hi. From the stoichiometry, I hope you can see that H2 reacted compared to Hi form. So if you are very weak at this kind of calculation, go through some of the topical playlists on equilibrium constant, on how to interpret what has reacted and what has formed, and how to do more examples of this kind of question, because we just never know when they will come up again, yeah? Alright? So how much of H2 has reacted? That is what you want to find. This is what you started with. I know it doesn't go to 0 because at equilibrium means I still have some of it, of the reactant. I have some of the product. Okay, that's what equilibrium means. Okay, so how much of that has reacted in terms of how much of it has formed? You started from nothing, you end up with 2y. So you have formed 2y mole of Hi. Bottom is for Hi. This is from balance equation. This is actual. Alright, so the mole of H2 reacted is equal to half times 2y, which is y. And you can also see that the mole of I2 reacted is also equal to the mole of H2 reacted, because 1 mole of H2 reacts with 1 mole of I2. So if you react this much H2, then this much of Y2 also reacts. So that is also equal to the mole of I2. So I don't need to do the same thing twice. So that will be A minus Y, because Y mole will have reacted. Now these are the concentration, these are mole, but these are all in the same volume. So when you multiply V total, multiply V total, then they're going to be the same, okay, because they're all in the same volume. I'm not taking anything out, alright? So our job is not complete. They want the Kc. So realistically speaking, I could have put a bit more space for myself. So if I use a different color, so based on the expression above, alright, so Kc is the Hi concentration, so it's 2y squared over A minus y squared And again, I'm not making my life easy for myself. You don't leave your answer like that. You always have to simplify, okay? I mean, I'm sure you know this from your maths classes, that you need to simplify your expression all the time, okay? So this is the simplified expression that I could get for the Kc. The expression for equilibrium constant from A part 2, basically this, can also be rewritten. So you want to make y the subject. Make y the subject. So basically they're giving you the answer, right? Make y the subject. Well, you don't have to, but I'm just saying that this is the answer. You can get Kc from this as well, alright? So if I start from here, this is not what the question is asked. I'll just do it anyway. So Kc times A minus y squared is equal to 4y squared. Am I doing this correctly? No, I'm not doing this correctly at all. No. It's not as easy as that. Okay, probably I don't want to do that. What I'll do is, because here you see a y on top and y at the bottom, it's not easy to make y the subject. What I'll do, see what I can do here. 2y plus y Kc is equal to A Kc. So A minus y Kc is equal to 2y. Then Kc is equal to 2y over A minus y. Then Kc is equal to 2y squared over A minus y squared. Oh, guess what? Kc is equal to that, right? So we can be sure that this is correct because I can go from here to here. Rather than going from here to here, that looks horrible, but I could easily go from here to here by just doing a bit of mathematics. That is not what the question has asked. I'm just saying that, you can check your answer given the answer is already here in a different form. So in an experiment, you remove A from a 1 dm cube flask. So your volume is 1 dm cube. The amount meaning the mole, okay, of hydrogen iodine gas were mixed together. Then you get the initial concentration as whatever they have told you just now, A mole per dm cube. You're allowed to come to equilibrium. This is at a particular temperature, 760 Kelvin. So room temperature is 298 Kelvin, that is 25 degrees Celsius. So that's 25 plus 273. Alright, so this one in degrees Celsius is 762 minus 273. Equilibrium concentration of iodine A minus y was then measured. Equilibrium concentration of iodine A minus 1. Look at it. You see, they are very, very generous actually. Yeah, they're very generous at telling you that this is the equilibrium concentration of iodine. Meaning to say, without doing this, you could have gotten the answer as well. So this is a very generous 1 mark. Okay, so you do it for various initial concentrations, and then you record the values in this table below. What do we want? We want y mole per dm cube to 3 decimal place. If you know A minus y, how can you get y? Alright, so if this is column capital A, column capital C, then F capital B, then column capital C is equal to A minus B, because you can try 0.200 minus 0.022, you're going to get 0.178, and you can also see A minus y is equal to A minus A plus y is equal to y. So to get y, you do this minus this, alright? So I'll do the rest of them. Make sure you know it's 3 decimal place. Maybe it's wise to just remind myself there. So this is one of those things your calculator give you 4.45. If you are not careful, if you don't think back on what you remind yourself, 3 decimal place, alright, based on the question. 0.548. So if you're looking at this on the screen, I really suggest you to actually get to compute this thing to see how careless you can be or how good you can be, and then you should really practice your putting in the graph as well, because that takes a bit of practice. Yeah, it's not like one day you just turn up and then you get very good at it. Okay, so very few people are actually gifted like that. I'm not gifted, so I have to do it the hard way through practice, which you know yourself if you're gifted or not. So give it a try and see how long it takes you. Alright, if it takes you long, practice a bit better so that it will take you shorter time with practice. So that was just for 2 marks for computing all of these to 3 decimal place. Next bit is a plot of graph of how the y mole per dm cube vary with a mole per dm cube. So this is our y-axis, this is our x-axis. Instead of me going back and forth to this table, what I'll do is I'll have the table of results on another piece of paper, and I'll start plotting this graph based on those values. That's what I meant by you should have calculated the value somewhere. Then you can start practicing drawing this graph with me and see how long you take. Alright, very stingy. Only 1 mark for plotting in the graph. That is very, very stingy. Anyway, when you see the graph, you see there's 1, so there's 0.5. This is also starting from 0, 0. There's 1, so there's 0.5. So since it's 1 mark, let me just get started without wasting any time. Alright, so it's plotting y against a. So 0.2 is 0.178. 0.2, so there's 0.5. So this is 0.1, 0.2, 0.3, 0.4. So 2 of these give you 0.1. 0.2 is 0.178. 0.2 is 0.178. Roughly is there. We'll give or take. 0.2 and 0.178. 0.5 and 0.45. 0.5 and 0.4, 0.45. 0.8, 0.548. 0.8, 0.548 is 0.55. That's the closest. 1 and 0.8. 1 and 0.8. 1.5 and 1.135. 1.5 and 1.135. Somewhere there. 2.1 and 1.53. 2.1 and 1.53, 2.8 and 2.148, 2.8, 2.148, 3.4 and 2.7, 3.4, 3.4 and 2.7, 2.5, 2.6, 2.7. 3.8 and 2.93, 3.8, 3.8 and 2.93, so that's close to 2.95, 4.2 and 3.33, 4.2 and 3.33, 3.3, so it's 3.3 is roughly there, and lastly 4.9 and 3.75, 4.9 and 3.75, 4.9 and 3.75. So that is 3.5. Between 3.5 and 4.0, this middle bit is 3.75, and then 4.9 is just 2 small square before that, because that is 4.5, so 2 small square before that is 4.9. Alright, so we can see there is a straight line. Okay, so there's quite a good straight line there. I'm gonna minimize this a little bit. When there is none of A, there will be none of Y. So we know this will cut through 0, 0. But what you do not do is do not put a cross there, because this is not a point given on the table. But you know you cut through 0, 0 because you can think about what happened. You can think about, so this is what you would do on your ruler. Best fit straight line. Best fit straight line, you want to fit the most number of points. Okay, that's probably my best fit straight line. So some of the points are going to deviate slightly, but when there is no A, and your A was your initial concentration, so if you don't put anything in, how can you get anything out at all? Alright, so that's why I cut through 0, 0, but we don't put a cross there because it's not a point on the table. Okay, so draw a line of best fit, which I just did. Determine the slope of your gradient. So if we go back to our graph, okay, it's not necessarily a point from the table, but it's about a point where the line passes through. Our line passes through 0, 0, so that it can be my one coordinate, 0, 0. And the second point, I'll probably go for something easy. Where is an easy one? That seems to be easy, so that is at 2.0. So this thing there, 2.0, and so that was 2.0, so there's 1.5, there's 1.55, so 2.0 and 1.55, okay. 2.0 and 1.55 is my other coordinate, so it's basically there, alright. But you have your own line, so you should use your own data, yeah. So don't be surprised that your value will be different slightly from mine, unless your graph was badly drawn, I guess, okay. So they just want the gradient, so the slope refers to the gradient. Remember, it was an upward slope. Upward slope means it will be a positive gradient, which I'm sure you know from your gradient classes in lower secondary mathematics. So use bracket in your calculation, because brackets are one of those things which are very, very important. I get that exactly. That is 2, 3 significant. So you might get more decimal place, but it's just down to what value you use. Doesn't matter really. Calculate the gradient, make sure it's 3 significant, and then that's it. So you gotta use your value of your slope, which is a gradient, and the equation in B to calculate Kp, and you must show working. What is your equation in B? The equation in B is y is equal to AKC over 2 plus KC. I'm just writing that out because I don't want to be flipping back and forth. Actually, I should cut that. So on your actual exam, you can flick back and forth between your paper, so you don't do what I do, obviously. So what was the graph you show? Your graph that you draw was y against a, alright? Y against a. So y against a. I hope you can see that is your y-axis. This is your x-axis. And then this means this bit there, it's basically your gradient. There is no y-intercept because there is no constant. Big C, y is equal to mx plus c. Alright, so this is your linear relationship there, because our line cut through the origin, so there's no constant there. It doesn't have a y-intercept bigger than 0, so that doesn't exist. So there's just the y-axis, there's just the x-axis on your graph. You plot y against a just now, so your gradient is just all that thing there, because there's a constant, there's a constant, there's a constant. At a constant temperature, your Kc doesn't change. Alright, so therefore your gradient is equal to Kc over 2 plus Kc. Do I want that? Yeah, I guess I can move that a little bit there. Then that can be there. Give me a bit more space to work with. So that's 0.775. That is your gradient from the previous question. So now really your job is make Kc the subject. So Kc is equal to 0.775. Use bracket, alright? I cannot stress that importantly. This whole thing multiplied by 0.775, and this is where a lot of students would have made a mistake. They thought it's just 2 times 0.775. No. This is a plus. This bring up the whole thing. It means this times this, alright? So you know expansion of terms from your, again, I keep on saying, your lower secondary mathematics. But you might have done this in upper secondary mathematics, I'm not sure. But you would definitely have done it in your mathematics before you come to A level. Alright, so Kc minus 0.775 Kc is equal to 1.55. I hope you can factorize this, or at least you can see there is 1 of it. So 1 minus 0.775 is equal to 1.55. Your Kc equal to 1.55 over 0.225. Okay, my working is getting a bit long now. In reality, if you are very good at maths, you can cut down a couple of these steps. But I'm not very good at maths, so so I'm showing everything. Okay, so that is square because it's 1.55 over 0.225. The whole thing square because now I move the square root to the other side. All right, or you can think about square both sides. When you square this, you will have no square root. Then when you square this, you get that. And you should give your answer to 3 sig fig because we used previous data. That was to 3 sig fig. 1.55 square, sorry, 1.55 divided by 0.225. Then you square that. Oops. Then I get 47. Maybe I shouldn't use that much space there. Maybe I can use the space here. Yeah, okay. Alright, so as long as it's labeled, yeah, as long as it's labeled, it should have been alright if you label your step properly. Because I don't feel comfortable writing the answer for one part in the lines of another answer, alright? That's 47.457. KC is roughly 47.5 to 3 significant figure, okay? You can cut down some of the steps. I was just showing all the steps because, like I said, I wasn't very good at math, so I don't want to make any mistakes, alright? Explain why, for safety reason, that you want to remove the A from the 1 dm³ flask. So we know that we had to remove that A, right? So if we have A, what does A contain? So A is a mixture of gases. Mostly is nitrogen and oxygen, which are diatomic, okay? So the oxygen can react with hydrogen from this reaction as a reactant. And I'm not sure if you know that hydrogen reacts with oxygen is exothermic reaction, so can be explosive. Just think about your reaction of sodium with water. You release hydrogen and the hydrogen reacts with oxygen in the air and it catches on fire, alright? So it can be explosive, especially at a high temperature. Because if you remember, you did the reaction not at room temperature. I talked earlier about when you read the question, you did it at 760 Kelvin. That is way higher, 760 Kelvin. So it's just for safety reasons, and you gotta outline why and how is it not safe. All right. Phew. So one of the experiments in B was repeated. You use a 500 cm³ flask. So this is a smaller volume than a 1 dm³ flask. Would that affect Kc? Well, I can tell you it wouldn't because only temperature can. So since you're just changing volume, you're not changing temperature, that would not affect it. But rate of reaction, yes, because changing volume means that you will change the pressure of the gases exerting on the wall. So this is a classic rate versus equilibrium. Instead of being asked in a theory paper, as you will have seen the topical playlist under chemical equilibrium, you will see there's a lot of questions that have been asked in the theory paper 4 or paper 2 on rate versus equilibrium type of scenario, but here is being asked in a paper 5 setting and is perfectly within their syllabus or their specification to ask you that. Alright, so firstly I can talk about Kc first. So value of Kc remain constant. They don't ask for explanation, they just ask you to state, yeah, remain constant, or you can use the word unchanged. Alright, because Kc is only affected by temperature. Alright, so your equilibrium position can change when pressure changes due to the change in volume, but only temperature can change the value. Alright, however, the rate, you go to a lower volume, so maybe I start explain first. With a smaller flask, with a smaller volume, 500 cm³ of the flask, the gaseous reactant collide more frequently. Can imagine when you have a big flask and a small flask. In a small flask, you have the same amount of stuff, right? You still have the same amount of, gases, but in a smaller volume, so they will collide more frequently, and therefore the rate of reaction is faster. And again, they don't ask you to explain. I don't know why I have spent some time explaining it. Ideally, it would have been enough if you just say rate of reactions get faster in that smaller flask, and value of Kc remain constant in that smaller flask because you are not changing temperature. Alright. Anyway, I mean, if you are in theory paper, you'll be expected to talk about collision frequency based on the changes in volume. You'll be expected to talk about only temperature can affect the value of Kc. They always ask this in a MCQ kind of question as well, yeah? So this is the last two questions on this paper 5 tutorial. In this question, they tell you that the reaction of hydrogen and iodine to form Hi is exothermic. Okay, so what effect would higher temperature do on the value of Kc? So we did say that only temperature can affect value of Kc. If I start by explaining it first, they don't ask for explanation again, they just want the effect. But I think it's easy if I start explaining it. The forward reaction is exothermic. The forward reaction release heat energy. Okay, that means when I increase temperature, what would the equilibrium do? The equilibrium will try to oppose the change. The equilibrium will try to decrease the temperature, but the equilibrium the system only knows to release heat energy. So to lower the temperature, to decrease the temperature, the reaction or the equilibrium will release less heat. How will the equilibrium release less heat? It will shift to the left to release less heat. That means to favor less of the forward reaction, it will favor backward reaction at higher temperature. When you favor backward reaction, you get lesser product, you get more reactants, and you also know that Kc can be affected by temperature. So because you favor backward reactions, so Kc value will decrease or decreases or get smaller somewhere along those lines as a result of the forward reaction being exothermic and your equilibrium favoring backward reaction, because your equilibrium will release less heat in order to counteract and oppose the increase in temperature by trying to decrease the temperature to shift backward to favor backward reaction to produce less product. Okay, so our graph, this is what happens. The equilibrium shift that way at higher temperature. What does our graph shows? Our graph shows y against a. So y against a. And what was y against a? You have the starting concentration of A mole per dm cube, and then you produce 2y mole per dm cube of Hi. Okay, so this is your product, this is your reactant. Okay, your product and your reactants. All right, not essentially exactly, but this represents the mole of the Hi, the concentration of the Hi produced, and we are producing lesser Hi. We are producing lesser Hi, and we'll have a bit more of the reactants. All right. So that means our gradient, which was a ratio of the product and the reactants, okay, so that would tell us that the gradient is slightly steeper because, slightly less steeper, because we will have lesser of the product, okay, compared to the reactant, because the value of Kc would have decreased. Okay, you don't use a different colored ink, you just use one color, and it doesn't matter whether I've drawn this or this or this, as long as you have a less steeper gradient. So this has a less steeper gradient because the steepness of the slope is lesser, so the gradient is lesser, so you get lesser product compared to your reactants for that specific concentration of your reactant. You have lesser of the product as a result of Kc being smaller. All right, so your Kc decreases as temperature increases, all right, because your fourth reaction is exothermic. So I should probably label it as, this is F part 1. So whatever, because everything will have been drawn in pencil, all right, so I would probably have to label it with F part 1 instead, okay, F part 1. But I should be very clear, because this is the one with crosses, this is the one with no crosses. Speaking of crosses, this looks really anomalous. Maybe I just check back this point. This is 2.1, 2.1 and 1.53, 2.1 and 1.55. Did it say 1.53? 2.1 and 1.53. 2.1 and 1.53. So that point is actually wrong as well, okay? So that should have been 2.1. Where's 2.1? 2.1. 2.1 and 1.55 is there. 1.5 is there. 1.53 is roughly there. Or maybe I was right. I don't know. Okay? But I mean, that's still pretty close. Anyway, so we already established that the value will change as temperature changes based on Lee-Chatelain principle. I drew the line, I labeled the line, draw and label the line at 1000 Kelvin. So I just labeled it F part 1, that should have been alright. So that's it on this paper 5 tutorial.